En 3, 2, 1, and when you watch.
Hello everyone, I'm Khadija Mukrim, UM6P student. Today we are here in a special program of the UM6P studio where we are covering the third edition of the Science Week. Today we are here and we are pleased to have one of our brilliant guests of this Science Week, Mr. Stephan Wolfram. Welcome, sir.
Thank you.
And we're pleased to have you today. And we would like to know more about you.
There's many things to say. I mean, I alternate between doing science and doing technology. I started out at a pretty young age doing physics research. I started publishing papers about physics when I was 15 or so, and got a PhD in physics when I was 20. For a while I was doing basic science. That led me to need technological tools, computational tools. So I started building those. Built my first big computer system back, it's terribly long ago now, 1981 type time frame. And then that led me to start doing basic science again. So I've alternated between doing basic science and doing technology about 5 times in my life. But my day job for the last 36 years, I've run a company, Wolfram Research, which is kind of spread out around the world, lots of places. And our primary mission is to do the best that can be done with computation for kind of all purposes. And for students, people may know about our product, Wolfram Alpha, which is used by lots of students around the world.
Yes, so I can see that it was an exciting and a very interesting career. So I know you've been leading so many researches. I would like to know, can you tell us about one of your researches and how it relates to the theme of complexity of this year of Science Week?
That led me to start looking at simple programs and how sort of a program picked, for example, at random, what does it typically do? And I made this kind of big discovery that even programs that are very simple in their structure can have very complicated behavior. And it seems like that's kind of the secret that nature uses to make most of the complexity we see. And it's something that, so that was a discovery of mine from the, early 1980s. And that kind of turned into a lot of science that a lot of people have done around this kind of idea of complexity from simple rules and so on. The thing that was kind of a foundation that many layers up we get to the things that I'm doing now about fundamental physics and about mathematics and so on. Those are things that were built on that foundation of complexity. But I would say that this idea of complexity is still very much not absorbed yet in the world at large.
So talking about ChatGPT, an example of complexity system which starts simplifying maybe tasks for people. What do you think of the ethical and philosophical consideration that may impact the scientific research nowadays?
Well, I mean, with AI, people say, we'll make a scientific theory of the ethics that the AIs should follow. Yes. This is doomed, because ethics is a human question. There's no sort of mathematical right answer to how ethics should work. Ethics is what people want ethics to be, so to speak. And one of the things people, perhaps in the sort of globalized world, people get a bit confused about is the idea that there's going to be sort of a single sort of code of ethics that applies for everybody everywhere. It's not true. And we see that as a practical matter in the world. And it's something that in these systems, it's one of these things where people are always hoping that there'll be sort of just a piece of software you can write that implements ethics, and then you're done. This is not the case. And in fact, this whole phenomenon of computational irreducibility has an effect there, because let's say you have rules for a system. I don't know, maybe it's a self-driving car, maybe it's some other kind of system. You say, I'm putting in these rules. Then I'm sure the system's just going to do the right thing. But in fact, there are always things you can't predict just from knowing the rules. There are always, and we see that, it's been something that we see in the construction of laws for humans. It's not, you don't write down a code of laws and then expect that will tell you about all possible circumstances in the future. You expect that you have to add patches to that and modernize things and so on over the course of time.
Yeah, exactly, sir. So, last but not least, in your opinion, how the study of complexity will be evolving maybe in the future and its potential impact in the scientific field and innovation?
One of the things that's a good and bad feature of the things that I do is I tend to build things which are pretty, they're sort of artifacts from the future. So there are lots of things that I did 40 years ago or something that people are just now, oh yeah, we now understand how this works. So it's kind of it's both personally fulfilling and frustrating that there are things that, I know we've already built that in 50 or 100 years, people will say, oh yeah, that's obvious. That's the way that's the way it has to work. But it isn't obvious yet. But it's something, so we can kind of see pretty clearly. So for example, one thing is the study of how simple programs behave, which is a field, I call it ruleology, study of what simple rules do. It's a field that is kind of a wide open field. There's a few hundred people who work on it these days based on stuff I did back in the early 1980s. But it is a field where it's tremendously important. It's the analog, in chemistry, 100 years ago or so now, people just went and discovered, how does this chemical compound work, that one work, that one work? And then somebody discovered, well, one of them is used for plastics, one of them is used for something else. Each one of these things gets an application. Ruleology is the same kind of thing, but it is a foundational kind of thing where those components get used to make algorithms, make molecular computing systems, make architecture, actually. The question is, what is the fundamental sort of, what do simple rules fundamentally do? And it's a foundational area. It's probably a more foundational area than pure mathematics, for example. And it's an area that's wide open. And it's an area that has the nice feature today that for, young people and so on, you can get into this area. You just have to know how to do, computer experiments. You have to have good judgment about what experiments to do and how to make conclusions from them. But it's not an area where there's hundreds of years of history that are built up that you have to learn before you can make new progress in the area.
So it's really amazing and mind-blowing for me, makes me want to learn more about it. But unfortunately, we'll have to say that we reached the end of our interview. It was really a very big pleasure for me as a student here and for our university, Mohammed VI Polytechnic here in Morocco, to have you and have this discussion with you. Thank you so much, Mr. Stephan Wolfram. Thank you. And see you in the next interview. Thank you.